Namaste everyone. Hope all of you are well and try to be safe everyone, because nowadays you are seeing the number of positive cases are increasing. So my humble request to each and everyone, please be safe. Now in the previous lecture I have explained you about the gaseous laws like Boyle's law, Charles' law, Avogadro's law, Gay-Lussac's law, after the ideal gas equation. I hope all of you have understand till the partial pressure, the Dalton's partial pressure. Now we will move ahead as each and every topic were covered in the previous video. So now after the ideal gas equation there was a great theory called kinetic molecular theory of gases. First of all, before starting this topic, there are few postulates about this topic, but I want to ask you something. Whatever we are studying, at least that thing should be in our mind. As for example, if I started the chapter called states of matter, right? In the states of matter, what things we have studied, that is more important. First of all, I have started with intermolecular forces, right? In the intermolecular forces, what we have studied about? We have studied about dispersion force or London force. Second, we have studied about dipole force. Third, we have studied about dipole induced force, right? After that, I have discussed you about the hydrogen bonding, and then I have discussed about the thermal energy, after then gaseous laws. In this gaseous laws, I have informed you about Boyle's law, Charles' law, Gay-Lussac law, after then Avogadro's law, and finally I have informed you about the ideal gas equation. And combined gas equation, right? This much things we have studied in the gaseous laws. After then, Dalton's partial pressure. Have you heard this word or not? Dalton partial pressure. And after then, mole fraction of partial pressure. Mole fraction. Right? This much things we have studied, and I hope all of you have understand in that lecture 1 and lecture 2. Till this topic we have already completed. Now the question is, after this what we have to study, right? After this our theory is kinetic. The word which we have introduced already in thermal energy. Why I have written these all the things? Because whatever the things you have learned in the previous lecture, the things are going to correlate with each other. So that's why, as I have written here, kinetic molecular theory of gases. The word kinetic molecular theory of gases. What do you mean by kinetic molecular theory of gases? Can you understand, or can you tell me what is this kinetic molecular theory? Have you ever thought about this word kinetic molecular theory of gases? See, after understanding all the gaseous law like Charles, Boyle's, Avogadro or Gay-Lussac, after understanding the concept, can you tell me, have you ever thought that what should be the properties of gases and how these gases will accommodate into the cylinder or any vessel? Just suppose this is a cylinder. In this cylinder, what are the properties of gases? These are the few gaseous molecules as you can see here, right? In this gaseous molecules, can you tell me what properties do gas have? This theory is especially about the properties of the gases only. Kinetic molecular theory of gases is just like a property of gases. Whatever the things you have already studied in the Boyle's law, Charles' law, Gibbs-Sachs law, Avogadro's law, ideal gas equation, the same thing, the properties we are going to discuss in this, in which the two properties very, very important. First of all, tell me, what the things are, as I have told you, volume is inversely proportional to pressure according to Boyle's law, right? Volume is directly proportional to temperature according to Charles' law. Volume is directly proportional to the number of atoms according to Avogadro's law. So according to this we have got an ideal gas equation, PV is equal to nRT, right? This was our ideal gas equation. Now I would just like to tell you, what about this intramolecular forces? The chapter begins with the intramolecular forces. So in the gaseous, you know very well why these gases do not have a fixed shape, do not have a fixed volume, because intramolecular forces means there is no attraction between the two atoms, between the two molecules. If there will be no attraction, just suppose they are attached with the cylindrical walls, no pressure with each other. But when you apply a pressure with the piston, what will happen? As you apply the pressure, what will happen? Now slowly volume decreases, because already we have studied volume is inversely proportional to pressure. So as you have applied a pressure, you have given a force of pressure, then what will happen? Can you tell me what will happen? Now the number of atoms are coming close to each other. Now the number of atoms are coming close to each other. As the number of atoms will come close to each other, hence the force of attraction will increase. As the pressure had increased, volume has decreased, number of atoms come close to each other, there will be some rules and laws. According to NCERT, you can see there are some of the postulates of the kinetic molecular theory. First of all, what is kinetic molecular theory? I just want to tell you, it is a model which specially observed about indicate the behavior of gases. Means what are the behavior of gases after applying all these laws? What are the behavior of gases? How do gas act as? So this theory is especially dealing the behavior of gases. How are the behavior of gases? So few are the assumptions, or you can say the postulates of kinetic molecular theory. First one is gases consist of a large number of identical particles, atoms or molecules that are so small, so far apart that the actual volume of the molecules is, or the molecular volume and actual volume of the molecules is negligible in comparison to the empty space between. They are considered as point masses. This assumption explains the great compressibility of gases. First theory is, if I just talk about volume of this gas and volume of this whole cylinder, so can you tell me it is negligible in comparison to the cylindrical and gases or atoms? All the gases are made up of same atoms and molecules, you know very well. If I talk about the oxygen gas, carbon dioxide gas, argon gas, any other gases if I talk about, so they are made up of same atoms and molecules. Now question is what? If we talk about the volume, if we talk about the mass, what is the mass of this whole cylinder and what is the mass of the single molecules? It is approximately negligible in comparison to the cylinder and comparison of one atom or molecule of gas. This is negligible. If they are negligible, then the compressibility will be the maximum. They can be compressed. It can be compressed or not. Just tell me that. It can be compressed or not. Definitely, as according to the Boyle's law only, as you have seen, that volume is inversely proportional to pressure. So as you can see here, the atoms and molecules can be compressed very easily. So the first postulate of this kinetic molecular theory of gases is that gases consist of large number of identical particles, atoms or molecules that are so small and so far apart, so the average that the actual volume of the molecule is negligible in comparison to the empty space between them. So they are considered as a point masses. This assumption explains the great compressibility of gases. This was the first postulate. Now we are moving towards the second postulate. There is no force of attraction between the particles of the gases at ordinary temperature and pressure. The support of this assumption comes from the fact that gases expand and occupy all the spaces availability to them. Just suppose, just I am giving you one example. When there are more than 50 benches and teacher doesn't accompanied or it has not suggested any student to sit on this particular places or this individual places. So what will happen when the student comes in the classroom? They can sit anywhere. If just suppose there are 10 students and 60 benches are there in the classroom, what will happen? Anywhere they can sit. As before the teacher comes, wherever they want to sit, they can sit. Similarly, if I talk about if the shape and size of the whole cylinder and the gases are very less in amount, if the number of atoms are very less, just suppose it is having 1000 liter occupying tendency of the atoms and gases, but if there are only 5 to 10 atoms, what will happen? They can go anywhere. As you can see, according to the first postulate, you have seen that there is a high compressibility, but if I talk about the number of atoms and the attraction forces, what will happen? Can you tell me? No attraction forces. If there is no attraction forces, then what will happen? The gases will expand all over the space available to them. Wherever they want, they can expand. So this was the second postulate of kinetic molecular theory of gases. Now we are moving towards the third postulate, that particles of a gases are always in constant and random in motion. If the particles were at rest and occupied fixed position, then a gas would have a fixed shape which is not absorbed. First of all, at an ordinary temperature and pressure, you know very well, they are not having any type of attraction between these atoms and molecules, according to the second postulate of this kinetic molecular theory of gases. Now if I talk about, just suppose if they are not attracting with each other, they are not having any attraction between these atoms and molecules, because wherever they want they can move into the cylinder, wherever they like in the whole box, the atoms wherever they want to move they can move. And why they are not having a fixed shape and size? Because the space is maximum. If the space is maximum, wherever they want, just suppose if the space would be just same cylinder is there but the space is only this much, then you can say these are the shape and size of these gases. This much is the same. Because here the space is maximum. They do not have a fixed volume, shape and size, because everywhere the randomly atoms and molecules can move. Just suppose if here I have applied a pressure, so this atom will try to move here, after the collision it will come here, again they will go there, wherever they want, because the space is maximum. The reason why do gases do not have shape, size, volume fixed? Because there is a lot of space. And if I talk about this, if I talk about any shape of the vessel or the surroundings, since there is a lot of space, that's why the gas do not have fixed shape, size and volume. So this was our third postulate. Now we are moving to the fourth postulate, that collision of the gaseous molecules are perfectly elastic. This means the total energy of the molecules before and after the collision remains the same. There may be exchange of energy between the colliding molecules. The individual energies changes, but the sum of the energies remains constant. If there were loss of kinetic energy, the motion of the molecules will stop and the gases will settle down. This is contrary what is actually observed. So just suppose after the collision, you will think just I am here. If I slap any student, means my energy has been wasted. But here, after the collision also, the energy is not going to change. Energy is going to remain the same. If energy would be changed, then all these gaseous particles, after the losing of energy, they will be settling down. Are you getting or not? Then they will get a fixed shape and size, which is actually not observed. So after collision also, they do not exchange their energy. They do not lose or gain their energy, because yeah, they can exchange with one another, but The total sum of energy, whatever I'm saying to you, just remember that word, the total sum of energy is not going to change. If the total sum of energy is not going to change, then what will happen? Can you tell me? It's going to remain the same, because first atom, second atom, third atom, after the collision also they are going to get the same energy. Now we are moving towards the sixth postulate. At any particular time, the different particles in the gases have different speeds and hence different kinetic energies. This assumption is reasonable because as the particles collide, we expect their speed change. Even if initial speed of all the particles was same, the molecular collision will disrupt the uniformly. Consequently, the particles must have different speed, which go on changing constantly. It is possible to show that though the individual speeds are changing, the distribution of the speeds remains constant at a particular temperature. Just suppose at an ordinary temperature, or we have given some temperature to this vessel, then what will happen? As we have given some temperature, so suddenly all the atoms will be in random. As these atoms and molecules will be in the random, they'll collide with each other. After the collision, what do you think? The speed of these atoms and molecules, individually, whatever their speed of the atoms and molecules were there, that will change. But overall, if I talk about, it's going to remain the same. Are you getting or not? Individually, all the atoms and molecules at their ordinary speed at whatever it was, it's going to change after the collision. But overall speed of the whole cylinder, if I talk about, it's not going to change. It's going to remain constant at a particular temperature. Last postulates of kinetic molecular theory: if a molecule has a variable speed, then it must have a variable kinetic energy. Under these circumstances, we can talk only about the average kinetic energy. In kinetic energy, it is assumed that average kinetic energy of the gaseous molecules is directly proportional to the absolute temperature. It is seen that on heating a gas at a constant volume, the pressure increases. On heating, the gas kinetic energy of the particles increases and they strike the walls of the container and frequently thus exerting more pressure. Kinetic theory of gases allows us to derive theoretically all the gases laws studied in the previous section, as the calculation and the predictions based on the kinetic energy of the gases agree very well with the experimental observation and thus establish occurrence of this model. So what we have studied, first of all, just suppose as we increase the temperature, means if we have increased the temperature, the pressure of the gases, the speed of the molecules, what will happen? These all the things will increase. They are not going to remain the constant. These things will increase. As these things will increase, what will happen? Can you tell me? As these things will increase, speed, temperature, pressure, all the things are increasing. Hence, the kinetic energy of the particles increases as they strike the walls of the container. Definitely, you just suppose I am having a ball, I am just throwing up and catching. As it strikes to the ceiling, what will happen? It will get a more force, it will come with a great force. Are you getting or not? Similarly, as these atoms will strike to the surface of the containers, their speed will increase, the temperature will increase, pressure will increase. So this was the kinetic molecular theory of gases. I hope all of you have understand about the kinetic molecular theory of gases. The more things which we are going to study, that is in the chemical kinetics chapter. In the chemical kinetics chapter, we will study about as any gas has got or treated with a different gas or intermolecular state, you can say, in the intermediate state, how they have changed in the arrhenius acid, what are the effects of this chemical kinetics. These are all the things we will study in chemical kinetics chapter. The rate of reaction, how increases and decreases, how are the half-life time period increases and decreases. These are all the things we will study in chemical kinetics chapter. So because why these things are important? Because you must know that what are the kinetic molecular theory. This is very important theory. Many of the students know about this all, and some of the students just got lots of these things that yeah, these things can be also done in the gases. So whatever the things you are getting to learn, I request everyone to understand the concept. As you understand the concept, what will happen? Similarly, you can comparison, you can come to the experimental values, you can come to the theoretical values. Whatever you are reading, it is 100% experimental. It is done with some of the gases, then only it is written in your textbook. Otherwise, it will not be written. Science is a pure subject of experiment. Remember this word. Science is not a subject of theory. Science is a subject of experiment. Especially if I talk about chemistry, it is 100% experimental subject. In chemistry, you can't say that, sir, everything is related to the theory and we study theory. Okay, students? After understanding the concept of kinetic molecular theory of gases, now just suppose that how these gases will behave according to the Charles law, Boyle's law, Gillisack law, or you can say the ideal gas and the real gas. What will be the difference between the behavior of these gases? The most important thing about the behavior and how do they deviate from the ideal gas. Means real gas and ideal gas, they both are two different. You know very well. See, a real person and an ideal person have a lot of defects. And if I talk about the real person defects and ideal person no defects. So there is a huge difference between the real person and ideal person. You can see some of the person just suggest that my ideal person is Swami Vivekananda or Abdul Kalam. We can't be, but we understand what is the difference between him and us, right? Similarly, here the behavior of real gases. The thing we are going to study is the behavior of real gases. What is this behavior of real gases? Our theoretical model of gases corresponds very well with the experimental observation. Difficulty arises when we try to test how far the relation is of ideal gas reproduce actual pressure temperature relationship of the gases. To test this point, we have plotted two graphs. You can see the graph is pressure volume versus pressure for the real gas and ideal gas. See, the real gases like hydrogen, helium, carbon monoxide, methane, these are the real gases, and ideal gases. This is the graph plot of the real gas and ideal gases, because at the constant temperature, pressure and volume will be constant according to the Boyle's law. If we keep the temperature constant, so what will happen? Pressure and volume will be also constant. And this pressure volume versus pressure graph, at all the pressure will be straight line parallel to x-axis. Why it will be straight line? Can you tell me? Such a plot constructed from the actual data of the several gases at 0 degrees Celsius or 273 Kelvin. So that's why whenever if I talk about the ideal gas equation, it will be parallel to the x-axis. This is a ideal gas graph. But if I talk about the real gases, carbon monoxide, methane, hydrogen, helium, so this is not parallel to the x-axis. The difference between the ideal gas and real gas, you can see the behavior or deviation from the ideal gas behavior. So this thing is the difference between the ideal gas and real gases. So as you can see, it can be seen easily that the constant temperature, pressure volume versus pressure plot of real gases is not taken into the straight line. There is a significant deviation from the ideal gas behavior. The two types of curves are seen in these curves for hydrogen and helium. As the pressure increases, the value of pressure volume also increases. And you can see there is second type of graph also here. This graph, this is a very, very important pressure volume graph. In this graph, what you are seeing? In this graph, the case of gases like carbon monoxide or methane, in this plot, first there is a negative deviation from the ideal behavior, and the pressure volume value decreases with increase in pressure and reaches to a minimum value characteristics of gases. After that, pressure volume value start increasing and the curves then crosses the line for ideal gas, and after then it shows the positive deviation continuously. It is thus found that the real gas do not follow ideal gas equation perfectly under all the conditions. So in this graph you can see that real gas do not obey the perfections of ideal gas. Similarly, here also you can see the real gas is not following the perfection between the ideal gas and whatever the terms and condition is of ideal gas equation in both the either pressure volume versus volume graph or pressure versus volume graph. In both these graphs, after understanding the concept of this graph, you will be able to see that real gas do not follow the terms and conditions of ideal gases. Right? Now, after understanding this all, now the deviation from ideal behavior also becomes apparent when the pressure versus volume becomes plot, as you can see in this graph as I have drawn, the pressure versus volume in the experimental data and the real theoretical values. Experimental data and real theoretical values, when you calculate from the Boyle's law or ideal gas law, then these plots is apparent that there is a very high pressure, that measured volume is more than the calculated volume. At low pressure it is measured and calculated volumes across each other. So it is found that the real gases do not follow Boyle's law. Real gases do not follow Boyle's law. Boyle's law is what? Pressure and volume. Tell me. As the pressure will increase, volume will decrease. But what happens in the real gases? It does not decreases. So you can say that the real gases do not obey the conditions of Boyle's law. So as you have seen the behavior of the real gases and the ideal gases, now let's talk about the Charles law. What Charles has said? Charles has said volume is directly proportional to temperature, right? Now Charles and Avogadro, volume is directly proportional to the number of atoms. So just see and just try to arise some of the question like, why do gases deviate from the ideal behavior? Here you can have a question in your mind, sir, why do these real gases, these all real gases, deviate the behavior from ideal gases? You can have this question in your mind now. Sir, if we are reading something about the ideal gas equation, then why it is not following? Why it is not obeying these rules and regulations? Why the temperature, pressure or volume has been different from the ideal gas equation? If you are saying about the pressure and volume, what the things are happening here in this graph, real gases and ideal gas? Second question you can have in your mind, sir, what are the conditions under which these gases deviate from ideal gas? You can have one more question, that what are the terms and conditions from which these real gases are deviated from the ideal gas law? We will get all these answers, whatever the question is in your mind, according to the kinetic theory of gases. We have read the two postulates that there is no force of attraction between the molecule of a gases. First is, there is no force of attraction between the gaseous molecules. There is no force of attraction. Because there is no force of attraction, since it is a gas, you know very well, if there is a no force of attraction, what will happen? If there is a no force of attraction, then gas, atoms and molecules can be anywhere. And second thing is, volume of the molecules of a gases is negligibly small in comparison to the space occupied by the gases. Means, if we talk about the whole cylinder and a single atoms, it is comparable negligible. So the two main postulates of kinetic molecular theory of gases is the reason why these gases deviate their behavior from the ideal gas. Why the real gases deviate these things? Because the atoms and molecules interaction force or attraction force is negligible. There is no attraction force between these gases, atoms and molecules. Second is, as I have said you, the second rules and regulation or your question answer is volume of the gases. The volume of a single atoms and molecules and the whole cylinder, if you comparison, they are also incomparable. It is negligible. So these are the two main things by which you can say that why there is a deviation from ideal gases to the real gases, or why these real gases behaviors are different from this ideal gas equation. Because in the ideal gas equation you have terms and conditions. As already in the kinetic molecular theory of gases, I have already explained you some of the postulates. You can just go through the postulates, and whatever the concepts you are not understanding in the kinetic molecular theory, read twice, read thrice. It is already represented in your NCERT book, whatever I have read. So as after understanding the concept, whatever I am telling you, try to note these things in your mind and just represent an experiment in front of your eyes. Just suppose this is a cylinder. In the cylinder, here there are some gases, atoms and molecules which are spread all over this whole surfaces, and as they are spread all over the spaces, so what will be the, as we keep the temperature constant, what will the relation of pressure and volume? If we keep pressure constant, what will the relation with the temperature and volume? If we keep pressure volume both are constant, what will the relation between the volumes and number of atoms? And similarly as in the Gay-Lussac law also, what will happen? Just suppose in your mind, and whatever the postulates are there, just conclude those postulates in front of your eyes. Yeah, it is real. Why these real gases and ideal gases are having different behaviors? What are the rules and regulations? Why they are not following the terms and conditions? Just like ideal gas equation, this theory's answers are already hidden in the kinetic molecular theory of the gas. After understanding the concept of these things, we'll move towards that. What are the factors that real gases and ideal gases, why do they change, and why is it close to each other also, and what are the factors that affects them?
But the ideal gas equation describes the behavior of gases based on experimental observations. To understand the behavior of gases at the molecular level, scientists developed a theoretical model called Kinetic Molecular Theory, KMT, or microscopic model of gases. Kinetic molecular theory is a set of 5 assumptions that describes the behavior of molecules in a gas. Let's discuss the assumptions and how they are justified in detail. Gases consist of a very large number of extremely small particles called molecules, which are in constant, continuous, random, and straight line motion. During their motion, they collide with each other and against the walls of the container. The pressure exerted by the gas is due to the bombardment of its molecules on the walls of the container. The molecules of a gas are separated from each other by great distances. Hence, the actual volume of all the molecules of the gas is negligible when compared to the total volume occupied by the gas. This assumption is true as gases are highly compressible. Hence, the actual volume of all the molecules of gas is negligible. Attractive and repulsive forces between the molecules of a gas are negligible as they are much away from each other. We can state that assumption 3 is true as gases expand and occupy the entire space available to them, showing the existence of weak intermolecular forces of attraction. Hence, attractive or repulsive forces between the molecules of a gas are negligible. Individual molecules do not gain or lose energy as a result of collision. Therefore, collision between molecules is perfectly elastic. This assumption can be justified because, during collision, the molecules do not settle down or slow down. The average kinetic energy of the molecules is proportional to absolute temperature. Assumption 5 is the result of the fact that when the temperature of a gas is raised, the molecules start moving faster. Thus, their individual kinetic energies increase, and hence the average kinetic energy increases. Based on these assumptions, an equation for pressure of a gas is derived as PV is equal to 1 by 3mnu squared. This is called the kinetic gas equation, where n is the total number of molecules in volume V, m is the mass of the gas molecule, and u is the root mean square velocity of the molecules. Let us now understand the gas laws in terms of the kinetic molecular theory of gases. First, let's start with Boyle's law. Consider a given amount of a gas in a cylinder fitted with a frictionless piston. According to kinetic molecular theory, pressure exerted by a gas is due to molecular collisions on the walls of the container. As the number of collisions increases, the pressure of the gas also increases. The average velocity of molecules is constant at a given temperature. When the volume of a gas is decreased, the space available for the movement of molecules decreases. Then, the number of collisions on the walls of the container increases, resulting in an increase in the pressure of the gas. This means, as the volume of a gas is decreased, pressure is increased for a given mass of a gas at a given temperature. This is Boyle's law. Next, let's take a look at Charles' law. Consider a given amount of a gas at non-atmospheric pressure enclosed in a cylinder fitted with a frictionless piston. When it is heated, according to kinetic molecular theory, the average kinetic energy of the molecules increases. Then, molecular velocities increase, thereby increasing the number of collisions with the walls of the container as well as the momentum of each molecule. As a result, the piston is pushed outwards. The volume of the gas then increases. Hence, at constant pressure, when the temperature of a given mass of a gas is increased, its volume increases. This is Charles' law. Next, let's move on to Avogadro's law. Consider equal volume of two gases under the same conditions of temperature and pressure. Since the temperature of the two gases is the same, according to kinetic molecular theory, the average kinetic energy of the gas molecules should also be the same. We know that the pressure of a gas depends on the number of molecules present This is Avogadro's law. Gases that obey the ideal gas equation are called ideal gases. The ideal gas equation is PV equals to nRT. If we plot a graph of PV versus pressure at constant temperature, then, according to Boyle's law, we should get a straight line parallel to the x-axis, as PV is constant at constant temperature for a fixed amount of gas. However, for a real gas, we find that the plotted line is not a straight line parallel to the x-axis. This shows that real gases, which include almost all the gases such as nitrogen, oxygen, hydrogen, and carbon dioxide, show a significant or an appreciable deviation from the ideal gas behavior. When we draw a plot between PV and P for these gases, we get two types of curves. The curves for hydrogen and helium, as shown, lie above the ideal gas curve, and these two gases show a continuous increase in PV with the increase in pressure. Whereas, for other gases such as carbon monoxide and methane, the PV value first decreases with the increase in pressure and reaches to a minimum. Then, this value increases with the increase in pressure so that it crosses the straight line of the ideal gas. Thus, a negative deviation is observed initially in the curve, followed by a positive deviation as shown in the graph. Let us observe the nature of the graph obtained for a real gas in a pressure versus volume plot. It is clear from the graph that at very high pressure, the volume occupied by a real gas is more than the volume occupied by an ideal gas. And at very low pressure, the volume occupied by both a real and an ideal gas are almost the same. Hence, at high pressure, these gases significantly deviate from the ideal gas behavior. Dutch physicist Johannes van der Waals gave an explanation for these deviations and modified the ideal gas equation in order to make it applicable to real gases. He observed that at low temperature and high pressure, the following two assumptions of the kinetic molecular theory do not hold good for the real gases. Assumption 1. There are no forces of attraction between gas molecules. Assumption 2. The actual volumes of the gas molecules are negligible when compared to the total volume of the gas. Let us see how the first assumption is modified and made applicable for a real gas by van der Waal.
So as you have understand the concepts that why do this real gas and ideal gases behavior changes. Hope all of you have understand the concept. In the next video we'll go further ahead. I hope all of you have enjoyed this video. If you have enjoyed this video, if you have understand the concept, then please don't forget to like and subscribe the channel. Share this video with your friends so they can be also benefited. That's all for today. Thank you very much. Have a great day.